Hold a single grain of sand on the tip of your finger and imagine that everything you have ever known, from every mountain on Earth to the blazing ball of fire rising in our morning sky, is just half of an ancient broken coin. For thousands of years, humans have stared upward and assumed our sun was a solitary monarch ruling an empty castle. But deep in the frozen graveyards of the outer solar system, trillions of icy relics tell us that our world was born as an identical pair. If you are drawn to the quiet, real wonders of the universe without exaggerated clickbait or empty filler, hit the subscribe button right now. We take you directly to the cutting edge of real space mysteries every single week, and joining our community means you will never miss a single breakthrough. When we look out into the night sky, we are naturally comforted by the idea of single stars living peaceful, lonely lives. Our sun sits right in the middle of our cosmic neighborhood, glowing with a steady yellow light, while 8 planets trace out clean, orderly circles around it. For generations, the simple picture led astronomers to believe that solitary stars were the normal, standard design across the universe. We grew up reading textbooks that portrayed our sun as a calm, independent father figure watching over its planetary family from the very beginning. Yet, as our space telescopes grew more powerful and turned their lenses toward the deepest corners of our galaxy, that comfortable assumption fell apart completely. In places like the Orion Nebula, the Taurus molecular cloud, astronomers uncovered vast nurseries where infant stars are constantly being born from giant clouds of freezing gas and cosmic dust. In these stellar cradles, single stars are not the normal pattern. They are the rare exception. Nearly every sun-like star in the galaxy is born locked in a gravitational dance with at least one companion star. Radio telescopes like the Atacama Large Millimeter Array in Chile have peered straight into the dense cores of these star-forming clouds. What they see is a repeating cosmic pattern. When a giant gas cloud begins to collapse under its own weight, it does not form a neat, single point of light. Instead, the swirling motions inside the cloud cause it to stretch, twist, and split into multiple dense cores. Sun-like stars are almost universally delivered as twins, triplets, or small litters of infant suns orbiting a shared center of gravity. This overwhelming observational evidence presented astronomers with an unsettling mystery right here at home. If practically every star that matches our sun in size, mass, and temperature began its existence with a twin partner, why does our sun appear so completely alone? Did our home star somehow defy the universal laws of star formation 4.6 billion years ago? Or was our solar system once home to a second sun that was violently torn away and lost to the deep darkness of space? To understand how our sun could have lost a sibling, we have to travel back in time to the very dawn of our solar system. 4.6 billion years ago, our region of space was an enormous, freezing expanse of molecular hydrogen gas, helium, and tiny grains of dust drifting through the Milky Way. A nearby disturbance, perhaps the shock wave from an exploding giant star, compressed this gas cloud and triggered a gravitational collapse that pulled matter inward at incredible speeds. As this vast reservoir of gas fell toward the center, friction and crushing pressure forced the core temperature to climb from freezing cold to millions of degrees. When the center reached roughly 15 million degrees, nuclear fusion ignited with tremendous power, forcing hydrogen atoms to fuse into helium and releasing an unimaginable flood of light and energy. That explosive ignition marked the birth of our home star, but modern physics tells us that the collapsing cloud would have had far too much spinning momentum to create just one star alone. Under standard hydrodynamic models, the swirling gas disk inevitably pinches into 2 distinct gravitational hubs. In a normal stellar nursery, this results in a wide binary star system, where 2 companion stars form side by side out of the exact same chemical soup. The 2 infant suns then begin orbiting each other, sharing the surrounding disk of leftover gas and rocky dust from which planets, moons, and asteroids eventually condense. For a long time, traditional astronomers pushed back hard against the idea that our sun ever had a twin companion. They pointed to the stable, circular orbits of Mercury, Venus, Earth, and Mars as clear proof that no second massive star had ever disrupted our inner neighborhood. Their reasoning was straightforward. If a massive second star had been orbiting anywhere near our planets, its intense gravitational pull would have warped their pathways into wild elliptical loops, or flung Earth completely out into the freezing void of interstellar space. That skeptical argument seemed nearly impossible to overcome until astronomers turned their eyes away from the warm inner planets and started examining the extreme, shadowy edge of our cosmic domain. Past the orbit of Neptune, beyond the frozen realm of Pluto and the scattered icy rocks of the Kuiper Belt, lies an enormous ghostly structure known as the Oort Cloud. The Oort Cloud is an immense spherical halo made of billions of icy comets and frozen boulders that wraps around our entire solar system like a massive, hollow bubble. Have you ever wondered what lies beyond the farthest planets we can see with backyard telescopes? Drop a quick comment below with your favorite outer space mystery, and hit that like button to help other curious minds uncover these hidden corners of our solar system. The inner boundary of the Oort Cloud begins roughly 2,000 astronomical units away from our Sun. To grasp that scale, remember that 1 astronomical unit is the distance between Earth and the Sun, which is roughly 93 million miles, or 150 million kilometers. This means the inner edge of this giant shell starts 2,000 times farther out than we are from our Sun, while its outer boundary extends past 100,000 astronomical units, nearly halfway to the next nearest star system. Here is where the traditional single-sun model runs directly into an impossible mathematical barrier. For decades, textbooks taught that all the icy comets inside the Oort cloud were merely leftover scraps, tossed outward by the formation of the giant planets. The theory claimed that as Jupiter, Saturn, Uranus, and Neptune settled into their modern orbits, their powerful gravity acted like a giant broom, flinging trillions of frozen rocks out into the far perimeter of the solar system. However, when modern astrophysicists used supercomputers to calculate the actual mass, volume, and density of the real Oort cloud, the traditional planetary broom model failed completely. 8 planets, even giant ones like Jupiter and Saturn, simply could not throw enough matter outward before clearing their own orbital paths. The true Oort cloud is far too massive and dense, containing vastly more frozen comets than our 4 gas giant planets could have ever launched on their own. In 2020, 2 astrophysicists from Harvard University, Dr. Loeb and Amir Siraj, set out to solve this missing mass paradox using advanced computer simulations. They wanted to discover what kind of cosmic setup could actually build an Oort cloud as massive and heavy as the one we observe surrounding us today. They ran thousands of complex digital simulations, testing single star systems, multi-star systems, and different star-forming nursery environments. What they discovered sent shockwaves through the astronomical community. The supercomputer models showed that the only realistic way our solar system could have assembled such an enormous ocean of icy comets was if our Sun had an equal mass companion star working alongside it during its infancy. A single sun acting on its own simply did not possess the gravitational reach or pulling power needed to gather that much loose material from the surrounding birth nebula. Think of it like trying to sweep up leaves in the middle of a massive windstorm. If one person stands alone in a wide yard holding a small rake, they can only collect a few scattered leaves before the rest blow away into the neighborhood. But if 2 people stand a short distance apart, holding a massive net between them, their combined reach and coordinated pulling power can trap hundreds of times more leaves blowing across the lawn. In our early solar system, the Sun and its companion star functioned as an enormous gravitational net. As our infant binary system drifted through the crowded stellar nursery, the combined gravity of the 2 stars reached deep into the surrounding clouds of gas and dust. Working together, they swept up trillions of wandering icy comets and trapped them permanently in the giant spherical halo that still encircles our entire system today. The mathematical precision of this dual star discovery was undeniable. When the researchers calculated the comet capture rate for 2 sun-like stars orbiting each other at a wide distance, the numbers matched the real-world mass and density of our Oort cloud almost perfectly. For the first time in scientific history, researchers held concrete physical proof that our solar system was born as a binary twin. Before we explore where this lost companion went, consider what our sky would have looked like from the surface of early Earth. The twin star would not have been a faint, distant speck hidden in the dark. It was a fully formed, radiant golden sun blazing across the sky. Early Earth was bathed in the glow of 2 distinct sunrises, dual shadows stretching across primitive volcanic landscapes, and 2 separate sunsets every single day. If you are fascinated by the idea of our planet once having 2 suns in the sky, take a quick moment right now to subscribe to the channel. Liking the video and turning on that notification bell ensures that independent, research-backed science content continues to thrive. Using the gravitational evidence preserved within the Oort cloud, scientists were able to estimate the physical properties and orbital pathway of this missing stellar twin. The companion was most likely an almost identical twin to our Sun, possessing a very similar mass, core temperature, and chemical composition. The 2 stars orbited their shared center of gravity separated by a distance of roughly 1,000 astronomical units. To put that distance into everyday context, Pluto orbits the Sun at an average distance of about 40 astronomical units. That means our Sun's twin was sitting 25 times farther away than Pluto, hovering right at the boundary where the inner solar system fades into deep space. Because the companion was positioned so far out, its gravity was strong enough to sweep up loose comets at the edge of the system, but too gentle to disrupt the tight, stable orbits of the inner rocky planets like Earth and Mars. This delicate balance allowed our planets to form in a warm, calm environment while the 2 parent stars built the outer defenses of the solar system together. But the nursery where our infant system spent its childhood was far from safe. Stars are not born in quiet, empty space. They emerge inside massive, turbulent clusters packed with hundreds or even thousands of other infant stars, drifting together through thick clouds of gas. Astrophysicists estimate that our solar system spent its first 100 million years drifting through one of these crowded stellar clusters. In such a dense neighborhood, stars are constantly brushing past one another, their invisible gravitational fields overlapping like giant competing nets. For a wide binary system separated by 1,000 astronomical units, this dynamic environment is extraordinarily dangerous. Astronomers originally assumed that binary stars either stayed locked together forever or collided in catastrophic fireballs. But modern orbital physics reveals a much more common fate known as stellar theft or gravitational disruption. All it takes is one single rogue star passing slightly too close to a wide binary pair, and the delicate gravitational leash holding the two twins together can be severed forever. Sometime around 4.5 billion years ago, as our young solar system was drifting through the birth cluster, a massive neighboring star made a close approach. The gravitational wake of this passing giant pulled hard on our sun's outer twin, stretching its orbit beyond the breaking point. In a brief moment of cosmic time, the gravitational bond snapped, and our twin star was ejected into interstellar space, cast adrift in the vast ocean of the Milky Way. This process of stellar disruption is now recognized as a standard chapter in the life cycles of most stars across our galaxy. Data gathered by the European Space Agency's Gaia Space Observatory shows that up to 80% of all Sun-like stars lose their original birth companions within their first few hundred million years. Our Sun did not fail to produce a family. It simply survived an ancient cosmic separation that left it to raise its planets in solitude. Did you know that the majority of stars in our galaxy might have lost their original birth twins just like our Sun did? Tell us in the comments what you find most surprising about this stellar separation, and share this video with a friend who loves exploring space mysteries. The sudden ejection of our twin star left behind a permanent record that extends beyond the Oort Cloud. In recent years, astronomers, mapping the extreme outer regions of the Kuiper belt, the ring of icy bodies past Neptune, noticed a series of deeply puzzling orbital anomalies. Several distant dwarf planets and icy worlds, including a famous object named Sedna, travel along extremely stretched egg-shaped pathways that tilt sharply away from the rest of the planets. Sedna travels on an orbit so extreme that its closest approach to the Sun is 76 astronomical units, while its farthest point takes it nearly 1,000 astronomical units into deep space. For years, scientists struggled to explain how an object could end up in such a severely elongated orbit without being completely thrown out of the solar system altogether. To explain these strange pathways, some astronomers suggested that a massive undiscovered world known as Planet 9 must be hiding in the dark outskirts of our system. According to this theory, the gravity of this unseen planet has been slowly tugging on distant icy bodies over billions of years, shepherding them into their unusual aligned orbits. Yet, despite extensive searches, using the most advanced infrared telescopes on Earth and in space, no direct visual trace of Planet 9 has ever been found. The binary twin model provides an elegant, physically sound alternative that explains these strange orbits without needing to invent an invisible ninth planet. When our Sun's companion star was pulled away by that passing neighbor, its massive gravitational field would have delivered a powerful one-time pull to the outer edges of the Kuiper belt. That parting gravitational kick would have naturally warped the orbits of objects like Sedna, freezing them into their bizarre, stretched-out shapes forever. Rather than hunting for a hidden planet that may not exist, scientists are beginning to view these tilted, off-center orbits as the physical footprints of our departed sibling. The strange paths of these distant frozen worlds are historical artifacts, preserved in the deep freeze of space like fossils that document the exact moment our twin star was ripped away from our home system. This realization brings us to an exciting investigation that is unfolding in real time across the scientific community. If our Sun's twin star was merely pulled out of its orbit and launched into interstellar space, it did not vanish or explode. Stars of our Sun's mass live for roughly 10 billion years, meaning that our lost sibling is still fully alive right now, quietly traveling along its own orbital path around the center of the Milky Way galaxy. Astronomers refer to stars born from the same gas cloud as solar siblings. Because these stars were created from the exact same batch of raw cosmic material, they share a distinct chemical fingerprint. They contain the exact same precise ratios of iron, carbon, oxygen, magnesium, and rare elements as our own Sun, allowing scientists to identify them even after billions of years of separation. In 2014, a team of researchers led by astronomer Ivan Ramirez at the University of Texas at Austin made an incredible discovery. By carefully analyzing the light spectra and chemical compositions of thousands of nearby stars, they identified a star named HD 162826, located about 110 light-years away in the constellation Hercules, Its chemical profile and age proved beyond doubt that it was born in the exact same stellar nursery as our Sun. A few years later, in 2018, another scientific team led by Vardan Adebekian at the Institute of Astrophysics and Space Sciences in Portugal discovered an even closer match. They located a star catalogued as HD 18632, situated roughly 184 light-years away in the southern constellation Pavo. This star is an almost identical carbon copy of our Sun, matching its mass, surface temperature, chemical recipe, and evolutionary age almost perfectly. While HD 18632 is confirmed to be a true solar sibling from our Sun's birth cluster, astrophysicists are actively working to determine if it is the specific wide-orbit twin that helped construct our Oort Cloud. The European Space Agency's Gaia Space Observatory has mapped the precise positions, distances, and three-dimensional velocities of over 1 billion stars. Using this massive dataset, researchers are building backward orbital simulations, rewinding the cosmic clock by 4.5 billion years to trace which star was once directly bound to our Sun. If tracking down our Sun's lost twin across billions of miles of space excites your imagination, make sure to subscribe and turn on your notifications right now. We follow these real-time astronomical searches very closely, delivering honest updates as new data arrives from our greatest space observatories. Finding our lost companion is far more than a sentimental search for a long-lost family member. It directly touches on the biggest question in modern science, which is how life emerged on planet Earth. When our world first condensed out of the swirling protoplanetary disk, it was a searing, molten ball of rock constantly blasted by intense heat. Under those extreme conditions, volatile elements like water could not condense, and were largely baked out of the inner solar system. Geologists and planetary scientists widely agree that the vast oceans covering our world today were delivered later in Earth's history. During a prolonged period of cosmic impacts, millions of water-rich asteroids and icy comets from the outer solar system rained down onto our cooling planet, filling the ocean basins and supplying the organic compounds necessary for the first living cells to assemble. This is where the role of our lost twin star becomes absolutely crucial to our own existence. If our Sun had been born completely alone, without a wide companion star to help harvest and trap that massive reservoir of icy debris in the Oort Cloud, our solar system's outer comet reserve would have been tiny or non-existent. Without that vast storehouse of frozen material on standby, the late delivery of water to Earth might never have occurred on the scale needed to form global oceans. By acting as a gravitational net during those critical first 100 million years, our twin star built the very storage vault that later made our planet hospitable to life. Every drop of water flowing in our rivers, filling our seas, and moving through our own bodies may be a direct legacy of a star that was torn away from us before the first single-celled organism ever formed on Earth. This revelation is also forcing astrobiologists to completely rewrite their rules for searching for habitable exoplanets around other stars. In the past, scientists searching for alien life focused almost exclusively on single stars like our modern Sun, assuming that binary systems were too dynamic, chaotic, and dangerous for life to ever develop. Worlds with two suns were often dismissed as science fiction environments where stable climate cycles could never take hold. Now, astronomers are beginning to realize that starting life in a temporary binary system might actually be a golden ticket for planetary habitability. The early presence of a twin star helps assemble a rich water reservoir on the outskirts of the system, while the eventual ejection of that twin allows the inner planets to settle into stable, long-lasting circular orbits where life can flourish undisturbed for billions of years. Temporary binary systems may represent the ultimate cradle for life in the cosmos. To fully grasp how wide binary stars shape their surrounding space, we have to look closely at the chemical makeup of primitive meteorites found right here on Earth. When scientists analyze ancient space rocks like carbonaceous chondrites, they find tiny microscopic grains of dust that are older than the Sun itself. These pre-solar grains contain chemical signatures that could only have been formed under very specific conditions of dual radiation and slow, mixed cooling. When two companion stars orbit one another inside a dense birth cloud, their solar winds push against each other, creating turbulent shock zones where gas and dust are compressed in unique ways. These compression fronts act like cosmic factories, forcing complex organic molecules, simple amino acids, and icy compounds to bond together in vast quantities. The presence of our twin star provided the extra energy and magnetic turbulence needed to forge the basic building blocks of organic chemistry long before the planets finished forming. Furthermore, the existence of our lost twin completely rewrites the story of how our gas giant planets formed their massive atmospheres. Jupiter and Saturn contain enormous amounts of hydrogen and helium, but they are also enriched with heavier noble gases like argon, krypton, and xenon. For decades, planetary scientists could not explain why these giant planets contain such high concentrations of noble gases, which only freeze out of space at temperatures below -400 degrees Fahrenheit. If Jupiter and Saturn had formed close to a single hot sun, those noble gases would have remained warm vapors that could never be captured by the growing planets. But in a wide binary system, the outer companion star creates a cold shadow zone in the outer disk, a vast deep freeze region where volatile gases can freeze onto solid ice grains. These frozen grains then drifted inward, feeding the growing gas giants with the exact chemical mixtures we measure inside their atmospheres today. The gravitational dance between the young sun and its companion star also explains the unusual tilt of our sun's equator compared to the orbits of the planets. The 8 planets of our solar system all orbit in a remarkably flat plane, like marbles rolling across a glass tabletop. However, the sun itself is tilted by roughly 6 degrees relative to that planetary plane, an odd misalignment that has puzzled physicists for over 200 years. If the sun and the planets formed from a simple, isolated spinning disk, the sun's equator should align perfectly with the orbital plane of Earth and Jupiter. But when you introduce a massive companion star orbiting at an angle during the first several million years, its gravitational torque naturally twists and tilts the surrounding protoplanetary disk. That subtle, persistent pull tilted the planetary disk by exactly 6 degrees before the twin star was stripped away, leaving a permanent cosmic tilt that remains frozen in our solar system today. What is even more incredible is what this means for the search for Earth-like planets around other stars in our galaxy. When NASA's Kepler and TESS space telescopes surveyed thousands of exoplanets, they discovered an enormous number of super-Earths and sub-Neptunes orbiting close to their parent stars. Our solar system is strangely missing any planets between the size of Earth and Neptune, creating an empty gap that makes our planetary layout look unusual compared to other systems. Astronomers now suspect that the presence and eventual ejection of our twin star swept away excess gas and dust from the inner solar system at a critical moment in planet formation. That gravitational clearing prevented our inner rocky worlds from ballooning into giant, thick atmosphere super-Earths, preserving Earth as a small, rocky, water-covered sanctuary with a thin, breathable atmosphere. Without the departure of our companion star, Earth might have become a suffocating gas world completely hostile to advanced life. To understand why this dual star birth is so fundamental, we must also examine the long-debated Nemesis hypothesis that captivated astronomers in the late 20th century. In 1984, paleontologists David Raup and Jack Sepkoski identified a statistical cycle suggesting that mass extinctions on Earth occurred roughly every 26 million years. Physicist Richard Muller proposed that a faint dwarf star named Nemesis was orbiting our sun at an extreme distance, periodically disturbing the Oort Cloud and sending deadly comets crashing into Earth. For decades, astronomers scanned the sky for Nemesis, searching with wide-field infrared telescopes like NASA's WISE satellite to detect any cold, red, or brown dwarf lurking in the outer perimeter. The surveys returned complete silence. No hidden dwarf star exists within our modern gravitational boundary. The Nemesis theory was officially declared dead, but it asked a question that modern binary formation models have finally answered correctly. The mistake of the Nemesis theory was assuming the companion star remained bound to our sun across all 4.6 billion years of Earth's history. The modern physical proof shows that our companion was not a tiny, dark dwarf star lingering in the shadows today, but a full-sized, sun-like twin that completed its entire job during the opening chapter of the solar system before departing forever. It was not a destroyer that triggered periodic mass extinctions, but a builder that gathered the raw materials for life and then stepped aside. This discovery also provides a clear explanation for the composition of the Kuiper belt and the strange boundary known as the Kuiper Cliff. At roughly 50 astronomical units from the Sun, just beyond the orbit of Pluto, the density of icy objects suddenly drops off dramatically, falling almost to zero. For years, planetary scientists expected the disk of icy debris to continue smoothly outward for hundreds of astronomical units, and the sudden, sharp edge remained an unexplained mystery. Computer models simulating the ejection of our twin star reveal that as the companion was pulled away, its final gravitational pass acted like a cosmic razor blade. It sheared through the outer protoplanetary disk, cleanly lopping off the outer edges of the Kuiper belt at exactly 50 astronomical units and scattering the remaining material inward or outward. The Kuiper Cliff is the physical scar left behind by that final gravitational cut. Have you ever considered that the shapes of the oceans and the edges of our solar system are direct physical results of a lost star? Tell us in the comments what you think about how our twin star shaped the architecture of our world, and hit that like button to help more space enthusiasts join the conversation. This structural impact also extends to the mysterious cratering records found across the surface of our moon, Mercury, and the moons of Jupiter. Planetary geologists have long studied an event known as the Late Heavy Bombardment, a chaotic period roughly 4 billion years ago when an intense surge of asteroids and comets smashed into the inner planets. The craters carved into the moon's ancient highlands are permanent scars from this violent era of impacts. While standard models suggest that migrating gas giant planets triggered this bombardment, binary star simulations show that the departing companion star played an equally vital triggering role. As the twin star was dragged outward, its shifting gravitational reach unsettled the orbits of millions of icy asteroids, destabilizing giant reservoirs of material and sending them plunging inward toward the sun. These impacts not only delivered essential water and volatile organic compounds to Earth's cooling crust, but they also created the deep hydrothermal basins where early microscopic life could gain its very first foothold. Consider what this means for the famous Drake equation, the mathematical formula developed by astronomer Frank Drake to estimate the number of active, communicative, extraterrestrial civilizations in the Milky Way. One of the key variables in that equation is the fraction of stars with planetary systems that can support life. For decades, scientists assumed that binary stars reduced the chances of life, lowering the estimated number of habitable worlds in our galaxy. With our new understanding of binary star nurseries, that equation must be reevaluated in the opposite direction. If temporary binary star systems are actually the primary engines that build massive comet clouds and supply water to newborn rocky planets, then the potential nurseries for life across the Milky Way are far more widespread than previously believed. The hundreds of billions of stars that formed in pairs and later separated may have all received the exact same water-enriching benefits that made Earth a living paradise. Right now, astronomers are turning the James Webb Space Telescope toward young star-forming systems like the Serpens Nebula and the Rho-Ophiuchi cloud complex to watch this process happening in real time. By analyzing the infrared light escaping from these dense nurseries, the telescope is capturing high-resolution images of wide binary stars actively pulling in icy dust from their birth clouds, confirming the exact mechanisms predicted by the Loeb and Siraj models. These observations show that the birth of planetary systems is far more interactive and interconnected than our old solitary models suggested. Planetary systems do not grow inside isolated bubbles. They are sculpted by the collective gravity of twin stars, passing cluster neighbors, and interstellar gas flows working together in a dynamic cosmic orchestra. Every breath of air we take, every cloud that drifts across our sky, and every river that cuts through a valley carries an ancient, unbroken connection to that missing twin star. We are made of material that was gathered, compressed, and protected by two distinct suns working in harmony 4.6 billion years ago, long before the first primitive organism ever opened its eyes on Earth. Somewhere out there among the spiraling arms of the Milky Way, our lost twin is continuing its silent journey through the galaxy. It still carries the exact same chemical blueprint as our sun, glowing with the same warm light and traveling along its own ancient pathway through deep space. It may even be warming its own family of rocky planets, holding water, delivered by the exact same cosmic net that made our world possible. We are not the lonely inhabitants of a solitary, accidental solar system. We are the survivors of an ancient cosmic family that separated billions of years ago, leaving behind physical signatures written in our comets, our oceans, and the tilted orbits of our outer worlds. As modern telescopes continue to map the galaxy with unprecedented precision, we're steadily closing in on the final location of our long-lost stellar twin. Thank you so much for joining us on this journey through space and time. If this story changed the way you look at our sun and the night sky, please hit that subscribe button, turn on notifications, and share this with someone who loves a great scientific mystery. What do you think happened to our lost twin? And do you believe it might have planets of its own with life looking back at us right now? Let us know your thoughts in the comments below, and we will see you in the next discovery.